Hi class, this is Mr. Morris. I want to go over solutions and mixtures with you. Now this would normally be a review topic, but because of COVID-19 you may or may not be familiar with some of these topics. So let's get started. Solutions are also called homogeneous mixtures. So a homogeneous mixture is another word for a solution. So homogeneous mixtures or solutions can be solid. Believe it or not, they can be solid, liquid, and gas. They can be any of those three states of matter or any combination of those three states of matter. In aqueous solutions, the solvent is always water. So we talk about aqueous solutions probably more than any other type. This word aqueous means that it is always dissolved in water. All right, the macroscopic properties. Oh, by the way, solvent. Remember, solvent is what it dissolves in. Solute is what dissolves. So in salt water, salt would be the solute. It's what's dissolving. And then water would be the thing that it dissolves in. The solvent. Okay, the macroscopic properties are properties that we can observe. So anything you can actually look at and observe. In a solution, the macroscopic properties are uniform throughout. It means they're the same throughout the sample. So we say it's same throughout. We're talking about macroscopic properties, what you could actually observe physically. We're not talking about the little bitty molecules, not talking about the molecular level, but we could actually observe. Consider a saltwater solution at any spots. The ratio, I'm sorry, let me start over there. Consider a saltwater solution at any spots or in any portion of it, the ratio of salt to water would be the same. It's going to look about the same. In a heterogeneous mixture, so heterogeneous is different than solution. Remember, solution and homogeneous are the same. Heterogeneous is different. The macroscopic properties differ or vary throughout the sample, so they can change throughout the sample. Consider a salad. Different spots in the salad it may have different compositions. So if you made like a tossed salad, you'd maybe have some more tomatoes on this side and fewer on the other side, or whatever. All right, molarity and dilution. That's a heterogeneous mixture, just to make it clear. Molarity and dilution. This is our molarity formula. Molarity is the moles of solute divided by the liters of the solution. Okay, the whole solution, the solute is what's dissolving in the solution. Right. Then we've got our dilution formula. This one over here on the right side is the dilution formula. M of stock times V of stock equals molarity of the diluted times the volume of the diluted solution. Sometimes you see it M1 V1 equals M2 V2. It means the same thing. All right, the equipment that we use to measure volume with more precision, so the things that we can use to get quite a bit of precision, are a volumetric flask, a graduated pipette, a volumetric pipette, a burette, a volumetric flask, and a volumetric pipette. Okay, those are really high, they have really high precision. Okay, these can only measure, so the volumetric can only measure, the volumetric flask and the volumetric pipette can only measure one volume. Okay. This over here on the right is an example of a volumetric pipette. It's got one mark on it, so it's only designed to measure one value. Now it's very, very accurate, very precise, but it can only measure one volume. Okay. These down here are called volumetric flasks. They don't have any graduations on it, only one mark. There's one mark They're very precise, very accurate, but they can only measure one amount, one volume. So volumetric flasks and volumetric pipettes can only measure one volume. A graduated pipette and a burette can measure a range of volumes. They're also they're also quite precise, quite accurate, but not quite as much sometimes. All right, so the equipment that we use to measure volume with less precision, so these are the things we're usually going to use if we care about how precise we are, but things that you can use if it doesn't have to be quite so precise, you can use a graduated cylinder or a beaker. Now that would be a very, very inaccurate or imprecise way of measuring, but you can measure volume in a beaker sometimes, okay? All right, how to make a solution using a solid solute. So the first thing we have to do is find out how much of everything that we need, okay? So we need to use this formula. Molarity equals N over V. Molarity equals N over V. That means molarity equals the moles over volume. And by the way, we find the volume in liters, okay? So it's moles over volume in liters. Now, if I want to know the mass of solid solute that is needed for something, and I know the volume, I know the molarity, I'm going to use this formula, and then once I find N, I'm going to solve for N, then I'm going to multiply by molar mass over 1 mole. Remember, molar mass grams divided by 1 mole. That's how you find the number of grams that you need, is by using this formula. Okay, that is if we're dealing with a solid solute. Okay. Our example here is I had to measure out some, and there's a procedure that we follow. I need to measure out the correct amount. I dump it in a in a volumetric flask. And then I put some water in, not enough to fill up to the line, but I put some water in, and then I swirl it, I stir it, I mix it up to get the solution nice and even until it's dissolved. Then I put more distilled water in until it's up to the mark and continue to swirl it a little bit to allow it to completely dissolve. That's the correct way to make a solution if I have a solid solute. Now, if I wanted to make a solution from a stock solution, that means I've got a solution, but I want it to be less concentrated. I want it more diluted. We're going to do something different in this case. We're going to find a certain volume. We're going to take a certain volume of our stock solution out and put it in the flask. Then we take that volume, a certain volume, we mix it with some water, and then we dilute it up to the mark. Okay? Same concept, but we're taking out a certain volume. Well, how do we find what volume of the stock solution I need? We have a different formula for that. That's M1 V1 equals M2 V2. To determine the volume of stock solution that is needed, and I'm looking for volume this time, not mass, I'm going to use M1 V1 equals M2 V2, where I'm solving, I'm sorry, not V2, I'm solving for V1. Okay, So I'm actually solving for V1. Note, when diluting an acid, the procedure is going to be changed a little bit. I want you to know that we always add acid to water. So in other words, what we're going to do is we're going to first put a little distilled water in the flask. Otherwise, the rest of the directions are the same. So I start, before I even take this out, I need to put a little bit of distilled water in the flask. When I say a little bit, I'm not talking just a few drops. I mean, it needs to be some water. It's just not enough to make it go above the line. All right, let's do a little practice with this. And this is where we're going to use the formula a little bit too. We want to describe the step-by-step procedure to make 500 milliliters of solution, 500.0 milliliters of solution of 0.277 molar KBr. So this is the result that I want. So I want this to be my V2 and I want this to be my M2. And I'm making it from potassium bromide crystals. So what state of matter is that? It's going to be a solid, and I want to know the mass. I need to decide how much I need to make. So what formula do I use if I'm trying to make a solution from a solid crystal? And I know the volume and I know the molarity. Well, I'm going to use M. And by the way, I said it's V2 and M2. I knew that was my final result. But now that I see that I just have molarity and volume, it's not M1 V1 equals M2 V2. It's the other formula, okay? So it's the molarity. I know the volume. I need to know the number of moles. Okay, so my molarity, the desired molarity is 0.277 molar KBr. The volume is 500.0 milliliters. And the number of moles is what I'm looking for. But really, do you have anything that can measure moles in the lab? Probably not. So I'm actually going to want to convert that into grams. So this is my planning stage right here. We're going to solve it, and then we're going to write down what our steps are. So again, I don't really need this V2 anymore, do I? It's just V. And it's not M2, it's just M. All right, let's solve. Molarity equals moles over volume, so I'm going to solve this by putting 0.277 equals in, I'm actually just going to completely cover that up because it's going to get in my way. There we go. In over 500 milliliters. Uh-oh, I need to change that into liters. Don't forget, if you want to change something to liters, you just move the decimal place 3 spaces to the left. And we'll drop that M and make it liters, okay? So we have 0.500 liters. Now I want to rearrange and solve for N. So N equals 0.277 times 0.500. 0.277 times 0.500, and I get 0.139 moles. 0.139 moles. Okay, that's great, but I want to find how many grams I need. So I'm going to use the molar mass, which hopefully we know how to find molar mass by now pretty easily. 0.139 moles of KBr. I need to multiply so that I have 1 mole KBr on the bottom. And then on the top, I'm going to have grams of KBr. And the molar mass of KBr happens to be 119.0. We're very close to that, 119.0 grams. So when you put that in your calculator, you're going to get 16.5. All right, so there's a lot of math. Now we want to put it in words because it says describe step by step how to make this. So how do I make this solution? First, going to weigh 16.5 grams of KBr and transfer into a volumetric flask. Second step, what am I going to do after that? I'm going to, oh, and by the way, the volumetric flask needs to be 500.0 milliliter flask. Okay. Second step is to add distilled water and mix. You can mix it by swirling it. Okay. And then the third step is dilute to the line, to the 500.0 milliliter line. And that's how I would make my solution. So when you do a problem like this, it says to describe step by step how to make that solution. First, you have to do some math to find how many grams you need. And then you weigh it, you add distilled water, you dilute to the 500.0 milliliter line because that's our end goal. All right, next problem. How would you prepare 100 milliliters of 0.250 molar solution of CaOH? Okay, but what are we making it from? From a 500 or 0.500 molar solution. All right, so this is the desired volume, V2. This is the desired molarity, M2. Okay, this is M1, it's my stock solution, because it's what I'm making it from. All right, so we can go ahead and set up our equation. What's the one thing I need to know? Well, I need to know V1. I need to know what my volume of the stock solution needs to be. Labeling the variables to the left would be great. I don't have a lot of room to do that, so as long as you label it somewhere, that's okay. All right, on this type of problem especially. Okay, so let's set it up. I'm going to go M1 V1 equals M2 V2. M1 is 500.500 molar. Sorry. M1, V1 is unknown, equals M2 V2, so we're going to put 0.250 times 100.0. Okay, we're going to multiply these by each other and divide by that in order to get the right answer, because I want to cancel, or I want to get rid of this and solve for V1. So V1 equals 0.250 times 100.0 divided by 0.500. All right, you put that in your calculator, you're going to get 50 milliliters. V1 is 50 milliliters, but I want to have 3 sig figs in my answer. So 50.0 milliliters. Make sure your units match the units of the other volume. They're milliliters. All right. Yeah, with this formula, because it's M1 V1 equals M2 V2, your units just have to match, okay? So now that I've done that, I actually know my volume that I need. So we can just answer the question directly. Step 1. We're going to measure .0 milliliters of the stock solution which is this 0.500 molar solution. Okay. Measure 50 milliliters of our stock solution in a pipette, either graduated or volumetric, but it needs to be pretty precise. Okay, we're not talking just a dropper bottle. Volumetric or graduated pipette. My second step is to dispense it into the volumetric flask. And what's my goal? I want to have 100 milliliters, so we're going to put it in a 100.0 milliliter volumetric flask. Add distilled water. Distilled H2O, and mix. All right, and our fourth step is to dilute to the line. Okay, make sure that you always have that last step. You're always going to dilute to the line. I know it kind of seems maybe silly to put that in there, but it's important because if you are mixing something up and you dilute it to the line before it's actually dissolved, and then you start swirling it, what will happen is sometimes it will actually swell up and sometimes it will actually go down. We'll talk about why that happens later, but you can end up with the wrong volume if you try to dilute to the line too soon. So you always swirl it when it's not quite full, and then we dilute to the line as the last step. All right, we've got a little bit more to do. Let's go to this page. And we're talking about, this is a lot more qualitative. We are talking about the structure of a water molecule. So just to remind you of the Lewis structure, when you're doing a Lewis structure, you need to think about how many valence electrons everything has. So water, that's H2O, so hydrogen has 1 valence electron. 1 times 2 is 2. Plus, and then oxygen, I've just got 1 oxygen. Oxygen has 6 valence electrons, so that's 6. So I have 8 valence electrons. Okay, so that's what I have to work with. Remember that most atoms want 8 valence electrons around them, but oxygen only wants 2, okay? So we're going to draw an oxygen, 2 hydrogen atoms, and connect them with bonds, okay? That's 2 4 electrons. I've got 8 to work with, so that gives me 2 4 6 8 electrons total. Okay, that's our Lewis structure. Now I could have drawn the hydrogens on any side, but for the molecular geometry to be correct, we're going to have hydrogen on either side like this, just the way I drew it, but I could have drawn it differently. Okay. And it's bent. Okay, the molecular geometry is bent. That is important because hydrogen is more positive than oxygen, so I have a partial positive charge, and then oxygen has a partial negative charge. Because of the molecular structure, the water molecule is polar. The side with hydrogen has a partial positive charge, and the side with oxygen has a partial negative charge. Now let's look at what that does with intermolecular forces. Now I'm assuming that we're probably a little rusty on IMF. We're going to spend a lot more time talking about this later, intermolecular forces. But I'm going to just kind of go through this briefly. By the way, this got moved. This belongs right here. I'll see if I can fix that before you guys have to fill this out. But the interaction in ionic should be with this. The interaction among water molecules. Okay, that's the interaction with the water molecules is what we're talking about right here. Anyways, it's a little messy, but we'll get it. And this is just one way of showing this. We have something called a crystal lattice structure. Talked about this in bonding. Okay, it's a rearranging structure of positive, negative, positive, negative, and it goes on and on. Positive, negative, positive, negative, positive, and it's alternating charges in this expanding crystal structure. This is a covalent compound. It's not held rigidly in a lattice structure like that. They tend to float more freely, especially since water is a liquid. But we still have these attractions between these. Okay, by the way, we call these hydrogen bonds. Remember, it's not a real bond, but these attractions between the H and the O are called hydrogen bonds. It's an intermolecular force, okay? It's the forces that attract molecules to each other, okay? There's an electrostatic attraction in this bond, and it's really, really strong, but it's still kind of an intermolecular force. It's right between intermolecular and a chemical bond. So, in our interaction between ions and water molecules in an aqueous solution, this is how it's formed. The water molecules will come close enough that they'll pull off some of those ions. And the sodium ions, the smaller ones, are surrounded by the negative sides of the oxygen in a water molecule. And the negative ions, which is chloride, will be surrounded by the white or by the hydrogen side of a water molecule. That's the positive side of a water molecule. This is an intermolecular force, okay? So this little arrow that I have right here, those are intermolecular forces, okay? Specifically, that is called an ion dipole attraction. We will spend more time talking about this in the IMF unit, but be aware of that. This is a attraction between an ion and a polar molecule, so it's an ion dipole attraction. So our solvation process, the process of dissolving, and this gets into energy and intermolecular forces. I'm going to briefly explain it, and when we get into intermolecular forces and energy, I'll probably come back and revisit this. I might have you watch this portion of the video again, and I'll explain it one more time. Okay, but when something like this dissolves, the first thing that happens is the water molecules have to come close enough that they actually break the attractive forces between the ionic, between these ions. Okay, so we're breaking electrostatic attraction between ions. Okay, now that's actually hard to do. That requires energy. Since it takes energy to make it happen, it requires energy. That means it's absorbing energy, so it is an endothermic process. We are also having to break the attraction between the water molecules. So we're breaking hydrogen bonds in H2O, or actually we should say between H2O molecules. That also takes energy, so it's endothermic. But then we are forming these attractive forces, these ion dipole attractions, and that is very favorable. It releases energy when that happens because it is favorable, so it tends to happen. It is an exothermic process. Okay, so the formation of bonds and formation of attraction, formation of IMFs is going to be exothermic. The breaking of IMFs is endothermic. Okay, let's go to the other side. This is a look at how ions break apart and dissolve in water. All right, then we have something like a sugar molecule in water molecules. Okay. By the way, sugar is covalent, but it's also polar. It's a polar covalent compound. Well, you see a clump of sugar here, and there's a certain amount of attraction between the sugar molecules. Okay. So I'm going to kind of abbreviate. In the case of sugar, there is actually some hydrogen bonding taking place. But I'm just going to talk about IMFs on this page because it depends on what type of substance it is. Okay. So one thing we have to do is we have to break IMFs between the solute molecules. In this case, our solute would be sugar. Okay, that requires energy, so it is endothermic. Okay, it absorbs energy. Then we also have to break IMFs, including hydrogen bonds, all the IMFs between H2O molecules. That is also endothermic. And then finally, we form IMFs between H2O molecule and solute molecules. And that's the part that's exothermic. So we started by breaking up these clumps and then separating some of the water molecules. So we're breaking the intermolecular forces between these and between these. And then we're forming new new intermolecular forces between the water molecules and the solute molecules. And that is the exothermic part. So that explains why it's favorable. I'm sorry, I was taking notes down where you couldn't see it, so I'm just going to set it there. You can pause the video if you need to copy that down. We're forming IMFs between H2O molecules and solute molecules, and that is an exothermic process. I know that was a lot of notes going over solutions, just a very quick, well, long, but that's an entire unit in one video. I want you to work on the solutions practice from the normal summer homework 4 worksheet, and we will be discussing this during next class.